Hello everyone. So this is the next video on linear algebra. Last class we discussed properties of the vector spaces and the subspaces and the linear span. So now we discuss the linear dependence and independence, then we move on to basis and dimension. So in this class we precisely focus on what is the meaning of linear dependence and independence. So let V of f be a vector space. Now consider any set of vectors, let me say v1, v2, v3, vn. So this is a set of vectors. These vectors are said to be linearly independent if I consider the linear combination of this then all the scalars must be 0, where I runs from 1 to n. If all the scalars are 0, then we say that it is linearly independent. Then what is linearly dependent? If it is not linearly, negation of linearly independent. What is the negation of linearly independent? Consider the same linear combination. Then here I have all alpha is 0. Here there exists at least one I such that alpha I is non-zero. If it happens, it is said to be linearly dependent. In the sense, see, the whole idea is this. When we say that the set is linearly independent, see, consider all the vectors. Let me say two vectors are there. So this is v1 and this is v2. Whether they are linearly dependent or independent, that is the question. See, when they can be made 0, when the linear combination can be made 0. That is the idea. That is alpha 1 v1 plus alpha 2 v2 equals to 0 when this is valid. See, I need to choose the scalar to be 0. Then only this vector will become 0, or else they are not 0. In the sense, if alpha 1 is 0 and alpha 2 is 0 means it is nothing but, if alpha 1 is 0 means what you will do? You will scale the vector v1 to be 0 vector. That means where it will lie? See, if I scale this vector, for example, I have vector, let me say v1, and its magnitude is 2 units. How to make the magnitude to 4 units? Scale it by 2. What is 2 into v1? It will be 4 units. Idea is clear. 2 v1 was there. I scaled it to, v1 was there, it was 2 units. I scaled it to 2, so I made it 4. Or else you can shrink it. I have 2 unit here. Okay. How to make it 1 unit? Divide it by 2, so it will become 1 unit. That means given a vector, you can always scale them. So can I make it 0? Can I make the magnitude 0? Take the scalar to be 0. So what it will do? If I scale it by 0 means it will just the 0 point. That is the origin. How about this? Alpha 2 to be 0. Then only it will become linearly independent. All scalars must be 0. If alpha 2 is 0, again what will happen to this vector v2? So already I nullified this to 0. v1 was nullified to 0. Again v2 was nullified to 0. Is it clear? So when you can nullify the linear combination, when you can nullify the linear combination of the vectors, you can nullify only at the origin. Later on, if you just come out from the origin, you cannot make them 0. In the sense, if you just come out from the origin, somewhere here if you stand means you cannot make them 0. When they will be 0? At the origin. In the sense, to be very precise, see, if I assume this and all v1, v2, etc., V1, V2, etc., Vn are brothers, or else they are brothers and sisters, and they are linearly dependent with the mother. They depend on mother only in the womb of the mother. This is the womb of the mother, the origin. Later on, once they evolve, 1 year child, 2 year child, they will become linearly independent. They become independent. And none of the brothers, if V1 is the elder brother and V2 is the next brother, then they are not linearly dependent. Your Anna Tamma andre avaru depend agala. When they will be dependent on mother only on the womb of the mother. That is called linearly independence. Everyone are dependent only. But when we are dependent, when we were child, we were dependent. When we were infant, we were dependent. In that sense, we say linearly independent. I should not say all these things, but to make you to understand, I am just explaining this. Actually, this linear combination view itself is different in physics view. If V1 and V2 are vector quantities, then what is alpha 1 into V1, alpha 2 into V2? That should be understood properly. But this is the vague way to remember these stuffs, that's all. What is linearly dependent? See, negation of this. At least one of the alpha is non-zero means somewhere you can have this vector alpha is non-zero. Here you need to come to the origin itself, but here it is not necessary. That's what negation of linearly dependent. One depends on the other means, see, this is the one vector V1, and let me consider the other vector V2. The dotted line is V2 and this is V2. Strictly speaking, V2 is some multiple of V1, right? For example, let me consider here I have 1 unit, here I have 1 unit, here I have 1 unit. So alpha is nothing but 3 units. So V2 is 3 times V1. If that is the case, they are linearly, one sits on the other, that is called linearly dependent. One is the scalar multiple of the other. Then we say that they are linearly dependent. Okay, that is the view. I said I was explaining the physics view of this. What is the meaning of alpha 1 V1 plus alpha 2 into V2 is 0. See, let us assume we are just, this is an object, or else consider it's some rock, and some people, V1 is one fellow who is pushing it, and V2 is the another fellow who is pushing it, and V3 is the another fellow who is pushing it. And he is pushing with some force, let me say alpha 1 times, he is applying some Newton of force. That is the force applied by this. And he is applying some Newton force to this object to move, and he is applying some force for this. So what is the resultant force? Alpha 1 V1, alpha 2 V2 plus alpha 3 V3. And the energy must, what is the force that he used, it must conserve. That is 0. That is the resultant. So they will move this object. That's what this linear combination is about. So if you just think about the physics view of this linear combination, it gives the exact picture likewise. These and all are vector quantities. See, definitely what else the force that you are applying, it has direction as well as it has magnitude. How many Newton force you are applying, that is the magnitude. In what direction you are applying the force, that will give you the direction. So it's a vector quantity in the sense it has both magnitude and direction. So in that sense, you can understand the view of what exactly that linear combination is about. But however, if we are some mathematical results are there, if you just think about those things, then it's enough to solve some problems. Is the idea is clear? Okay. Now, I have one remark here which says this. So this is about what else I took in the beginning was a finite dimension. So I took V1, V2. How many vectors are there? N vectors are there. Here also I took 2 vectors, V1 and V2. Here also I took 3 vectors. That means I am just considering only the finite number of vectors. What is the case if the vector space is of infinite dimension? So any infinite subset of V, that is consider any infinite vectors, is linearly independent if consider every finite subset. If it's every finite subset is linearly independent, then the set is linearly independent. Otherwise, it is linearly dependent. So this is the idea. If I have an infinite set V1, V2, Vn, etc., then consider the finite subset of this. Consider the finite subset of this. And if it is linearly independent throughout for any finite subset, then we said that the infinite set itself is linearly independent. If it is not linearly independent, we say that it is linearly dependent. So the well-known examples I'll just try to give. In Rn, consider the basis elements like E1 is 1, 0, 0, 0, E2 is 0, 1, 0, likewise En is 0, 0, 1. 1 is at the nth place. So these are linearly independent. How they are linearly independent? Just take R square. What is this E1 and E2? E1 is 1, 0 and E2 is 0, 1. So it is nothing but the unit vector. See, 1, 0 means in the x it is 1, y it is 0. It is 1, 0 and it is 0, 1. So it is I cap, j cap in the physics point of view. Whether they are linearly dependent or independent, just make them to 0. When they will be 0? They will be 0 at the origin. That is 1, 0, 0, 1. So take the determinant, it is 1, minus 0, it is 1. If it is non-zero, we say that it is linearly independent. If it is equals to 0, we say that it is linearly dependent. This idea is clear. So these vectors are linearly independent. Next. So we will think about these examples. So I have some remarks here. See, if the set S, V1, V2, V3, Vn is linearly independent, then it never contains zero vectors. Then S does not contain zero vector. Why this is the thing? See, I will just consider two vectors, then I will consider zero vector. So to be very precise, V1, V2 be the set, or else some V3. So I have, let me say, I am working in R square. Let me visualize everything in 2 dimension. So what is V1? V1 is, let me say, this vector. V2 is this vector. If V3 happens to be 0, where it will be? So this vector sits on some vector, scalar multiple of the other. Getting my point? That's what we had observed in the last example. See, I was giving here only. V1 was there. So V2 is linearly dependent because it is the scalar multiple of the other, in the sense one vector lies on the other vector. So one is the scalar multiple of the other. If it is zero vector means, see, zero vector sits on the other vector. You should ask me one question, sir, how this vector is approaching 0? It's nothing but the position vector. Point, you just make the point, let me say A comma B is this and this is C comma D, and just project it to the origin. Just make it to come from the origin. This is called the position vector. V1 is called the position vector, V2 is called the position vector. This idea is clear, from the origin. So where is that zero vector? If I consider V3 to be 0, where this zero vector will be? It lies on the origin. That means this vector sits on both V1 and V2. That means they are linearly independent. So if I have zero vector, linearly dependent. If I have zero vector in any set, it is linearly dependent. Keep that in mind. If zero vector is there, it implies it contains if the set contains 0 vector, it implies it is linearly dependent. So if I claim that this is linearly independent, none of the vectors must be 0 vector. So S does not contain 0 vector. This idea is clear? Next thing. See, this is important. Let A be subset of B. If A, the smaller set, is linearly dependent, then the larger set is linearly dependent. That is, every superset, that is B, of a linearly dependent set is linearly dependent. So this must be understood. Third one, let A be subset of B. If B is linearly independent, that is, if the largest itself is linearly independent, then A is linearly independent. That is, every subset of linearly independent set is linearly independent. So sometimes they may ask the question, which of the following is true? So these statements must be clearly understood. Okay. Then the fourth is, let me consider the set S to be V1, where V1 is non-zero. Whether it is linearly dependent or linearly independent is the question. Take the linear combination. Alpha 1 into V1 is equals to 0. Already we know V1 is non-zero. So what must be 0? Alpha 1 must be 0. So I have only one scalar here because I have only one vector. So if all the scalars are 0, that means I have only one scalar, so that is 0. That means this implies it is linearly independent. So a set containing single non-zero vector is linearly independent, always. So a set containing single vector is linearly independent. Idea is clear. Next thing is, what can you say about a vector space as a set? If I consider the vector space itself as a set, let S is equals to, where V is the set of all vectors over F. Then what can you say about that set, whether it is linearly independent or linearly dependent? See, idea is clear. Whether it contains 0 vector, so 0 element is there. If it contains a 0 element, then it is linearly dependent. So vector space as a set, it is linearly dependent. Then the next remark is, if A1, B1 and A2, B2 are from the ordered field R square, when we say that they are linearly dependent or independent, take the determinant, that is A1, B2 minus B1, A2. If it is non-zero, we say that it is linearly independent. If it is equals to 0, we say that it is linearly dependent. The idea is clear? Okay. Then the next thing is, consider the vector space f of x. It is nothing but set of all polynomials over the field f. Then consider this set 1 x square x cube. So it's a set of all polynomials, means you need to understand what is a polynomial. So degree must be defined. This idea is clear. It cannot go infinitely, because polynomial means degree is defined always. Idea is clear. So if I consider this, whether it is linearly dependent or linearly independent is the question. So just consider the linear combination of this: alpha 1 into 1, alpha 2 into x, alpha 3 into x square equals to 0. Then this 0 is nothing but, see, can I make this, can I say alpha is 0 for all I? because equate the constant term here, coefficient of constant term 1 into 0. So if I equate alpha 1 is 0. Equate the coefficient of x 0 into x. So alpha 2 is 0. Equate the coefficient of x square 0 into x square. So alpha 3 is 0. For all alpha I you will get 0. So in the sense all these scalars are 0 means it is linearly independent. This idea is clear? So that's what, although this set is infinite, we can think about linear dependence and independence. That was the first remark I had explained. Next remark is, see, if V1, V2, V3 is linearly independent, then consider the linear combination of this V1, alpha V2, beta V3, V2, V3 is linearly independent. This idea is clear? That is, P implies Q. Sometimes some will give in this way. This is equivalent to showing not Q implies not P. What is not Q? Negation of this. That is, V1 plus alpha V2 plus beta V3, V2 V3 is linearly dependent, implies V1 V2 V3 is linearly dependent. So that is the another remark. Then the set 1x 1 plus x square, whether it is linearly independent or linearly dependent is the question. See, already I have 1 here, x is there. But here I have one more term, that is x square. So because of this term, extra term x square is added to this 1 and x, it is linearly independent. It is linearly independent. Or else you can just think about the determinant of this. How to think about the determinant? 1x, 1 plus x square. Then take the derivative of this 0, 1, it is 1 plus 2x. Then take the determinant 0, 0, it is 2. So since it is triangular matrix, the determinant is nothing but the product of the diagonal, it is 2, it is non-zero. Differential equations, we define it to be Wronskian of the functions. So if the determinant value of the differentiation of the each term is non-zero, we say that it is linearly independent. That is one way of understanding. Or else think in this way, if two fellows are there, if additional fellow is coming who is not in the list, then it is linearly independent. Idea is clear? Already I have 1 and x here, it's okay, but I have one intruder, that is x square. Idea is clear? You can say, sir, it is x into x. That is not possible in vector space. Alpha into x is possible. Or else x plus x is possible. You cannot say, you cannot multiply x into x. That is not defined in the definition of the vector space. Because external composition is this, internal composition is this. V1 plus V2 is defined. V1 into V2 is not defined. Idea is clear? And this is the standard theorem which we studied in our undergraduate level. So I will just try to think of this. See, we consider the V1, V2, Vn are the vectors. If it is linearly independent or linearly dependent, only two possibilities are there. If it is linearly dependent, you can say then, if it is linearly dependent, then this set is the linear combination of preceding vectors. So that is a known result. Whenever V1, alpha 1 V1 plus alpha 2 V2 plus alpha n Vn is equals to 0. Linearly dependence means at least alpha I is, one alpha I is non-zero. Let me assume that is alpha k, where k comes in between. Okay, here I have alpha k vk. So if alpha k is non-zero, so what I will do is alpha k vk equals to, I will just shift everything to this, minus alpha 1 v1 minus alpha 2 v2 minus alpha 3 v3 minus alpha k minus 1 vk minus 1 plus alpha k plus 1 vk plus 1 etc. plus alpha n vn. So divide it by alpha k. So alpha k, so this is, I will say alpha k. Since alpha k is non-zero, I can divide. So what I will do, I will denote it by this by beta 1 v1. I will say this is beta 2 v2. I will say this has beta 3 v3. So it is similar to that beta n vn. So alpha, this is vk. Vk is nothing but the linear combination of the preceding vectors. This idea is clear. So that's what we observe from this. Then yes, so we have, let me say, some vectors v1, v2, vn, and v is there, where v is the linear combination of v1, v2, vn. This idea is clear. I took the vectors and v is the linear combination of these things. That means v can be expressed as linear combination of these fellows. This idea is clear. Then if I think about this set, then it is linearly dependent. Why? Because of this fellow v. Since it is the linear combination of all these vectors, it is linearly dependent. That's what we had observed in the last theorem. If it is a linear combination of the preceding vectors, then it is linearly dependent. Idea is clear? If v doesn't belongs to linear combination of this v1, v2, vn, then what is the situation? Then it is linearly independent. Idea is clear? That is, if I consider S to be v1, v2, vn, and if v does not belongs to L of S, then the set vn including v is linearly independent. That's what I stressed here. Then if in the set v1, v2, vn, if vi equals to vj for I does not equals to j, that means if any two vectors are equal, then it is linearly dependent. Why? Because one is the scalar multiple of the other. For example, v1 equals to v2 agogbudute. Again, v1 is 1 into v2. So one is the scalar multiple of the other, means it is linearly dependent. That's what we had observed. Idea is clear? Okay. Then we move on to basis of the vector space in the next class. Thank you.